What we've seen so far is how to use divide and conquer in a clever way to multiply large integers. So for n-bit integers, we were able to multiply, compute their product in time better than order n squared. A similar idea applies to matrices as well. What we're going to do now is multiply polynomials. And to do this, we're going to use the beautiful divide and conquer algorithm known as FFT. FFT stands for Fast Fourier Transform. So here's the setup. We have a pair of polynomials a of x and b of x. For the polynomial a of x, we'll denote its coefficients as a0, a1, a2, up to an minus 1. So it's of degree at most n minus 1. And for b of x, we'll denote its coefficients as b0, b1, up to bn minus 1. And it also is of degree at most n minus 1. Our goal is to compute the product polynomial, c of x, which is a of x times b of x. And the coefficients of c of x will denote as c0, c1, up to c2n minus 2, since the degree of c of x is at most 2n minus 2. Now recall that the kth coefficient of the polynomial c of x, so this is denoted by c sub k, this is obtained by taking the constant term for a of x, this is a0, times the coefficient for the kth term of b of x, this is bk. So I look at a0 times bk, and I add that to the other possibilities, a1 times bk minus 1, and so on, up to ak times b0. We want to solve the following computational problem. We're given the vector of coefficients defining a of x, and we're given the vector of coefficients defining b of x, and we want to compute the vector of coefficients for the product polynomial c of x. Now this vector c is known as the convolution of a and b. So this star symbol denotes the convolution. Let's take a quick quiz to make sure you're familiar with multiplying polynomials. And let's consider the polynomial a of x, which is 1 plus 2x plus 3x squared. And b of x, let's define as 2 minus x plus 4x squared. So the vector of coefficients for a of x is 1, 2, 3. And the vector for b of x is 2, negative 1, 4. And now compute the convolution of a and b. The solution to this problem is 2, 3, 8, 5, 12. To get the x cubed coefficient, 5, we obtain it in the following way. Multiplying 3x squared by negative x, we get negative 3x cubed. Multiplying 2x by 4x squared, we get 8x cubed. Adding these up, we get 5x cubed. Once again, the general computational problem that we're considering is, given this vector of coefficients for a of x, and this vector of coefficients defining b of x, we want to compute their convolution, c. Now a simple algorithm for computing this convolution is going to compute each of these coefficients in turn. Now there are order n coefficients. How long does it take to compute each coefficient? Well, a naive algorithm takes order k time to compute the kth coefficient, because there are k terms, order k terms that we have to sum up. This is going to lead to an order n squared time algorithm to compute all of the order n coefficients of the polynomial c of x. What we're going to do now in this lecture is an order n log n time algorithm for computing this product polynomial c of x, the convolution of a and b. Before we dive into the algorithm, let's take a look at a few of the many applications of convolution. One important application is filtering. So here we have a data set of n points. What we're going to do is we're going to replace each data point by a function of their neighboring points. This is used for such things as reducing noise or adding effects. Let's take a look at a more detailed example of filtering so it becomes clearer. In mean filtering, we have a parameter capital M, and we replace the data point yj by the average, the mean, of the neighboring 2m plus 1 points. And we do this for all j. Now this smooth data set y hat can be viewed as the convolution of y with a vector f. The vector f is this vector of size 2m plus 1. So to smooth the data set in this way, we compute its convolution with this simple vector f. Now of course we can smooth in more sophisticated ways. For example, we can replace this vector f by a Gaussian function. In this way, points nearby yj are given more weight. In particular, a Gaussian filter uses the following vector. This quantity z is just a normalizing factor, so that the sum of the entries in this vector sum up to 1. Now there are many other filters one might consider. A different type of filter one might consider is Gaussian blur. This is used to add some visual effect to an image, in particular to blur an image. In particular, Gaussian blur applies a two-dimensional Gaussian filter to an image. Now let's get back to our original problem of how do we compute the convolution of a pair of vectors. And let's look at some basic properties of polynomials. Consider the polynomial a of x. There are two natural ways of representing the polynomial a of x. The first way is by its coefficients. This is the vector a that we've been considering so far. A second way is by looking at the value of this polynomial a of x at n points. So we take n points x1, x2 up to xn, and we evaluate this polynomial a of x at these n points. The key fact is that a polynomial of degree n-1 is uniquely determined by its values at any n distinct points. So that this statement makes intuitive sense, the example to keep in mind is that of a line. A line is a degree 1 polynomial, and a line is defined by any 2 points on that line. And in general, a degree n-1 polynomial is defined by any n points on that polynomial. The vector of coefficients is a more natural way to represent a polynomial. However, the values are more convenient for the purposes of multiplying polynomials. We'll see this in a second. Now what FFT does is it converts from coefficients to the values and values to coefficients. So it does this transformation between these two representations of the polynomial. And the point is that coefficients is a more convenient way to represent the polynomial oftentimes, but the values are more convenient for multiplying polynomials. So we'll take the coefficients as input, we'll convert them to the values, we'll multiply the polynomials, and then we'll use FFT to convert it back to the coefficients once again. One important point is that FFT converts from the coefficients to the values, not for any choice of x1 through xn, but for a particular well-chosen set of points, x1 through xn. And part of the beauty of the FFT algorithm comes from this choice of these points x1 through xn. Before we dive into FFT, let's take a look at why the values are convenient for multiplying polynomials. One of the key ideas for multiplying polynomials is that multiplying polynomials is easy when we have the polynomials in the values representation. So suppose that we know the polynomial a of x evaluated at two endpoints, x1 through x2n, and we know this polynomial b of x at these same two endpoints. Then we can compute the product polynomial c of x at these two endpoints by just computing the product of two numbers for each I. So c of xi is the product of the number a of xi and b of xi. This is just a number, and this is just a number. Since c of xi is just the product of two numbers, it takes order 1 time for each I, and therefore it takes order n total time to compute this product polynomial. Now why do we take a and b at two endpoints? Well, c is a polynomial of degree at most 2n minus 2, so we need it at least 2n minus 1 points. So 2n points suffices. The summary is that if we have the value of these polynomials a of x and b of x at n or 2n points, then we can compute this product polynomial at these same points in order n total time. So what we're going to do is we're going to use FFT to convert from the coefficients to the values. This is going to take order n log n time to do this conversion, and then it'll take order n total time to compute the product polynomial at these two endpoints. And then we do FFT to convert back from the value of c of x at these two endpoints back to the coefficients for c of x. And that again will take order n log n time. So let's dive in now to see how we do FFT, which converts from the coefficients to the values. Now here's the smaller computational task that we're focusing on now. We're given this vector, a. These correspond to the coefficients for the polynomial a of x. And we want to compute the value of this polynomial a of x at two endpoints, x1 through x2n. And the key point is that we get to choose these two endpoints, x1 through x2n. How do we choose them? Well, that's our main task. A crucial observation is suppose that the first n points are opposite of the next n points. In other words, xn plus 1 is negative x1, xn plus 2 is negative x2, and so on. The last one is x2n is negative xn. Let's suppose that our two endpoints satisfy this property, which we'll call the plus minus property. And let's see how this plus minus property is useful. Once again, the plus minus property says that the first endpoints are opposite of the next endpoints. And let's see how this plus minus property is useful for recursively computing a of x at two endpoints. Let's look at a evaluated at the point xi and a evaluated at the point x n plus I. Since we're assuming the plus minus property, these 2 points are opposites of each other. Now let's break up this polynomial a of x into the even terms and the odd terms. Even terms are of the form a 2k times x raised to the power 2k. Since the power is even, this is the same for xi and negative xi. So these even terms are the same for the point xi and the point xn plus I. Now what about for the odd terms? Well, since it's an odd power, it's going to be opposite for xi and xn plus I. Now given this observation about the even terms and the odd terms, it makes sense to split up a of x into the even terms and the odd terms. So let's partition the coefficients for the polynomial a of x into those coefficients for the even terms. Let's call this vector a even. And into the coefficients for the odd terms. Let's call this vector a odd. So given this vector of coefficients for this polynomial a of x, define a even as the coefficients for the even terms and a odd as the coefficients for the odd terms. Then we can look at the polynomials defined by this vector of coefficients. This vector a even defines this polynomial a even of y. I've used the variable y to avoid confusion with a of x. Notice that a2 is the quadratic term in a of x, but in a even, it's the linear term since it's the second coefficient. And similarly, a4 is going to be the quadratic term. Similarly, this vector a odd defines this polynomial a odd of y. Notice that the degree of these two polynomials is n over 2 minus 1. So we took a polynomial a of x of degree n minus 1, and we defined a pair of polynomials of degree n over 2 minus 1. How does the polynomial a of x relate to the polynomial a even and the polynomial a odd? Well, notice if I take the polynomial a even and I evaluate it at the y equals x squared, then I get the even terms of the polynomial a of x. Similarly, if I evaluate the polynomial a odd at the point y equals x squared, then I get the odd terms, except it's off by 1 in the exponent. So I multiply it by x. So a of x is equal to a even evaluated at the point x squared plus x times a odd evaluated at the point x squared. At this point, you should start to see the semblance of the idea of the divide and conquer approach. We started with a polynomial of degree n minus 1, and now we've defined a pair of polynomials of degree n over 2 minus 1. So we went down from n to n over 2, and we got two subproblems, a even and a odd. And if we want a at a point x, then it suffices to know a even and a odd at the point x squared. So we got two subproblems of half the size. Now the degree of this polynomial a of x went down from n minus 1 to n over 2 minus 1 for these two smaller polynomials. However, if we need a of x at two endpoints, we still need a even and a odd at two endpoints, the square of these original two endpoints. So the degree of these polynomials went down by a factor of 2, but the number of points we need to evaluate them at hasn't gone down by a factor of 2 yet. This is where we're going to use the plus minus property. Given this polynomial a of x, we've defined this pair of polynomials, a even and a odd. They satisfy the following identity. A evaluated at the point x is equal to a even evaluated at the point x squared plus x times a odd evaluated at the point x squared. Now let's suppose that the two endpoints that we want to evaluate a of x at satisfy the plus minus property. So the first endpoints are the opposite of the next endpoints. So let's look at a evaluated at the point xi and a evaluated at the point xn plus I. Because of the plus minus property, this is a evaluated at xi and a evaluated at negative xi. Plugging this into our earlier formula, we have that a evaluated at the point xi is equal to a even evaluated at the point xi squared plus xi times a odd evaluated at the point xi squared. And similarly, for a evaluated at the point negative xi, we have it's equal to a even again at the point xi squared minus xi times, again, a odd at the point xi squared. So notice, to get a at these two different points, we need a even and a odd at these same points. Our conclusion is that if we're given a even and a odd at these endpoints, y1 through yn, which are the square of these two endpoints, notice that since these two endpoints satisfy this plus minus property, the square of these two endpoints are these endpoints. Then in order n time, we get a evaluated at these two endpoints. In particular, to evaluate a at the point xi, it takes order 1 time given the value of a even at this point and a odd at this point. And similarly, to evaluate a at the point x n plus I, it takes order 1 time, given the value of a even at this point and a odd at this point. In order to get two endpoints which satisfy the plus minus property, we're going to choose points so that the second n are the opposite of the first endpoints. What happens in the next level of the recursion? Then the points we're considering are the square of these two endpoints. So these are the endpoints, which are x1 squared up to xn squared. And we want these endpoints to also satisfy the plus minus property. Let's assume that n is a power of 2. Then we need that y1 is the opposite of yn over 2 plus 1, and up to yn over 2 is the opposite of yn. What does this mean in terms of x? This means that x1 squared is the opposite of xn over 2 plus 1 squared. But the square of a number is always positive. So this is a positive number, and this is a positive number. So how can they be opposites of each other? Well, it's impossible if we're working with real numbers. The only way to achieve this is by looking at complex numbers. So we can easily achieve the plus-minus property at the top level of the recursion. But for all further levels of the recursion, in order to achieve the plus-minus property, we need to look at complex numbers. So let's do a quick review of complex numbers, and then we'll see the appropriate choice of these two n numbers. We saw that we need to consider complex numbers for our choice of the n or two endpoints where we evaluate the polynomial a of x. Here I'll give a brief review of the relevant concepts regarding complex numbers. Some of you may get a bit scared at the use of complex numbers, but the mathematics involved is fairly simple, so don't get intimidated at all. And the final algorithm that we get is very simple and very beautiful. We have a complex number z, which is a plus bi. A is the real part, and b is the imaginary part. It's often convenient to look at complex numbers in the complex plane. In the complex plane, one of the axes corresponds to the real component, and one of the axes corresponds to the imaginary component. So for this number a plus bi, we look at a in the real axis, b in the imaginary axis, and we look at this point ab. This number z corresponds to the point ab in the complex plane. Now there's another way to describe this point, this number z. It's called the polar coordinates. In polar coordinates, we look at the length of this vector from the origin to this point z. Let's call r the length. And we look at this angle, theta. This number z in polar coordinates is r comma theta. Just as we had two representations of a polynomial, either the coefficients or the values, we also have two representations of a complex number, either with the Cartesian coordinates ab or the polar coordinates r theta. Now it turns out that polar coordinates are more convenient for certain operations, such as multiplication. Before we delve into properties of polar coordinates, let's review some basic properties. First off, how do we convert between polar coordinates and complex Cartesian coordinates? Well, if you remember a little bit of trigonometry, you'll recall that a, this length a, is equal to r times cos theta, and this length b is equal to r times sine theta. So this gives us a way to convert between Cartesian coordinates and polar coordinates. Now there's a third way of representing complex numbers. This is given to us by Euler's formula. This gives us a quite compact representation of complex numbers. The basic fact is Euler's formula, which says that cosine theta plus I times sine theta equals exponential of I times theta. Then we can multiply both sides by r, and then we have that this number z, this complex number z, equals r times exponential of I times theta. The basic idea of the proof of this Euler's formula is by looking at the Taylor expansion of exponential function, cosine, and sine function. As we mentioned earlier, polar coordinates are convenient for multiplication. Let's consider an example. Consider z1 and z2, a pair of complex numbers, and let's look at their product. Let's say that z1 in polar coordinates is r1 theta 1, and z2 in polar coordinates is r2 theta 2. Now let's look at the product of these polar coordinates. We simply multiply the lengths, and we add up the angles. Now suppose that I have a point z. I have a complex number z, and I want to look at its opposite. So I want to look at negative z. So this corresponds to multiplying z times negative 1. What is negative 1 in polar coordinates? Here's the point negative 1 in the complex plane. It's a distance 1 from the origin, and it has angle 180 degrees, or pi. So its polar coordinates are 1 comma pi. And let's say z is this point at polar coordinates r comma theta. Then negative z corresponds to the product of r comma theta times -1 in polar coordinates, which is 1 comma pi. Then using this above rule, we have that -z is at the polar coordinates r comma theta plus pi. So the point -z is the reflection of the point z. It's just the same distance from the origin. It's a distance r from the origin. And instead of going an angle theta, we go an angle theta plus pi. So if you view the complex numbers in the complex plane, it's easy to find their opposites by looking at their reflection. Now we're going to consider the numbers which are known as the nth complex roots of unity. Let's break this down. So by unity we mean 1. Instead of nth roots, let's consider the case n equals 2. So we're looking at square roots of unity. The square roots of 1 are 1 and -1. Now consider the case n equals 4. So we're looking at the fourth roots of unity. What numbers raised to the fourth power equals 1? Well, if we're looking at real numbers, the case is 1 and -1. But if we look at complex numbers, we have more considerations. Notice that I and -i, if we raise them to the fourth power, we also get 1. So the nth roots of unity for real numbers are just 1 and -1. But if we look at complex numbers, then there's much more to consider. In general, the nth complex roots of unity are defined as those numbers z's, those complex numbers z, where when we raise z to the nth power, we get 1. As we just mentioned, for the case n equals 2, the square roots of unity are the numbers 1 and -1. So it doesn't make any difference whether we're doing real numbers or complex numbers for this case n equals 2. For the case n equals 4, the fourth roots of unity are the four numbers 1, -1, and in addition, I and -i. Now what are the eighth roots of unity? And in general, what are the nth roots of unity? Now we're trying to find those z where z raised to the power n equals 1. Now let's draw the number 1 on our complex plane. What is this point in polar coordinates? It's distance 1, obviously, from the origin. What's the angle? The angle is 0. It's also 2 pi, or 4 pi, or 6 pi, or 2 pi times j for any integer j. And note j can also be negative number. So the angle is any multiple of 2 pi. Now let's say z equals the point r theta in polar. We're looking at those z where z raised to the power n equals 1. So it equals 1 comma 2 pi j. Recall the expression for multiplying two complex numbers in polar coordinates. So look at z raised to the power n. So z is r comma theta, so z to the n is r raised to the power n. And then we add up the angles, so we get n times theta. Now we're assuming this equals 1. So what does r equal and what does theta equal? Well, r raised to the power n equals 1. So then we know that r equals 1. So what does that mean? That means that all the complex roots of unity lie on this unit circle, this circle of radius 1. Where do they lie in this circle? Well, we got to look at the angle. N times theta equals 2 pi j. Solving for theta, we have 2 pi j over n. Let's take the case n equals 8 and see what this looks like on the unit circle. The case j equals 0 corresponds to angle 0, so this is the point 1. That's good because we know that the point 1, the number 1, is an nth root of unity. Let's look at j equals 1, so we got 2 pi over n. What does this correspond to, this angle 2 pi over n? It's like you took the whole pie, the whole circle, and you subdivided it into equal slices. For the case n equals 8, this angle is pi over 4. So this is the point 1 comma pi over 4. J equals 2 corresponds to this point, which is I, which is 1 comma pi over 2. Next point is 1, 3 pi over 4. Then we get 1 pi, which is -1. Then we get 1, 5 pi over 4, and so on. Notice that when we get to j equals 8, we repeat. We get back to this point 1. And j equals 9, j equals 10, and so on. So notice there are n distinct values, and what we're doing is we're starting at the point 1, and we're taking step sizes of 2 pi over n. And what we just saw are that the nth roots of unity correspond to the points in polar coordinates 1 comma 2 pi over n times j. J equals 0 corresponds to this point, which is 1. Then we take step sizes of angle theta, where theta equals 2 pi over n. This gives us j equals 1, j equals 2, and so on, and we keep taking these equal sized steps around the unit circle. Let's introduce a little bit of notation to make it more convenient for expressing these nth roots of unity. So let's let omega sub n denote the point corresponding to j equals 1. So it's the one right here. So this is omega sub n. Now what does the next point correspond to? Well, we just doubled the angle. So it's just the square of this point, omega sub n. And the next one is going to be the cube of this point. And the jth point is going to be the jth power. So the last one is going to be omega sub n to the n minus 1th power. And then we have omega sub n to the nth power, which is the same as omega sub n to the 0 power, which is the number 1. So the nth roots of unity are the following n numbers. It's omega sub n to the 0 power, to the 1th power, to the square, to the n minus 1th power. These n numbers in polar coordinates are 1, 2 pi over n times j, where j varies from 0 to n minus 1. And recall Euler's formula, so this number omega sub n equals e raised to the power 2 pi I over n. So the jth of the nth roots of unity, omega sub n raised to the jth power, where j varies between 0 and n minus 1, is e raised to the power 2 pi I times j over n. Now we saw that for the case n equals 2, the square roots of unity are the points 1 and minus 1. For the case n equals 4, we also have the points I and minus I. So we have the 4 points 1, I, minus 1, minus I. This corresponds to going around the unit circle in step sizes of space pi over 2. Then for n equals 8, we further subdivide the unit circle. Now we go step sizes of pi over 4. And then how do we get the points for n equals 16? We further subdivide. So this corresponds to omega sub 16. The next one is omega sub 16 squared. And notice that it's also omega sub 8. It's the first one of the 8th roots of unity. And this point I is omega sub 16 to the 4th power. It's also omega sub 8 squared. It's the second one of the 8th roots. And it's the first of the 4th roots. So take the nth roots and square them. And let's suppose that n is a power of 2, as in these examples. So what happens when you take the 16th root squared? Well, this guy goes there. This one goes there. This one goes there. This one goes there. What do you get? You get every other one of the 16th roots, which are the 8th roots. So the 16th roots squared are the 8th roots. And when n is a power of 2, the nth roots squared are the n over second roots. The other key property is this plus minus property. Take this point omega sub 16. What is the opposite of it? It's this point right here. This is negative omega sub 16. It's also a 16th root of unity. Which one is it? Well, this is the first, this is the 8th, this is the 9th. This is the point omega sub 16 to the 9th power. And in general, for even n, omega sub n to the jth power is opposite omega sub n to the j plus n over 2. By going an extra n over 2, I'm going an extra pi around, so I'm getting the reflection of that point. There are two key properties of the nth roots of unity which we're going to utilize. The first holds for even n. The nth roots satisfy the plus minus property. This was the key property for our divide and conquer approach. The first n over 2 of the nth roots of unity are opposite of the last n over 2. In other words, omega sub n to the 0 power equals negative omega sub n to the n over 2. And in general, omega sub n to the jth power equals negative omega sub n to the n over 2 plus j. So the nth roots of unity look like a perfect choice for our divide and conquer approach because they satisfy the plus minus property. The second key property holds when n is a power of 2. If we look at the nth roots squared, we get the n over second roots. So if we take the jth of the nth roots, so omega sub n to the jth power, and we square it, so in polar we're taking the point 1, 2 pi over n times j squared. So we simply double the angle. So we get the point 1, 2 pi over n over 2 times j, which is omega sub n over 2 to the jth power. So the jth of the nth roots squared is the jth of the n over second roots. And similarly, if we take the n over second plus jth of the nth roots and we square it, well, this is just the opposite of this. So when we square the negative of it, we get the same thing. So why do we need this property that the nth roots squared are the n over second roots? Well, we're going to take this polynomial a of x and we want to evaluate it at the nth roots. Now these nth roots satisfy the plus minus property, so we can do a divide and conquer approach. But then what do we need? We need to evaluate a even and a odd at the square of these nth roots, which will be the n over second roots. So this subproblem is of the exact same form as the original problem. In order to evaluate a of x at the nth roots, we need to evaluate these two subproblems, a even and a odd, at the n over second roots. And then we can recursively continue this algorithm. Now we're all set to do our FFT algorithm. And the endpoints where we choose to evaluate the polynomial a of x are the nth roots of unity.